Or actually still morning here. I want us to do a little bit of chapter 2 review, but I also want us to get started with our 2.6 unit. Obviously, this is not going to be on the test, but just so that we can kind of keep up with our calendar.
Good morning again, good afternoon. Students, you have 4A lunch. It is now time for you to go to the cafeteria. That's students that have 4A lunch, so teachers and students have 4A lunch.
So we're going to start off with 2.6 notes. Let me put that link on the Teams page, so in case you don't have the notes in front of you. So I started, I have another page for related rates, so it's on that link there. Okay, so with related rates, it's going to feel like a kind of a natural extension from implicit differentiation. So what I mean by that is, remember with implicit we had dy over dx, but now we're going to have time is going to be the independent variable. It's going to be the driving force for all these problems. So instead of d over dx or dy over dx, now we're going to have d over dt. And every variable is going to be impacted. So if it's radius, it'll be dr dt. If it's x, it'll be dx dt. If it's area, it'll be dA dt. So every variable is now going to have this impact, this additional piece we have to include for its derivative. Okay, so this is also an application of implicit differentiation, being able to find the derivative of a variable with respect to time t. So let me list out the steps. The order of the first three is not that important. In fact, as long as we're gathering information and what we need, we can kind of we don't have to follow that order. We can kind of just gather information as we see it. So, but here in general is what we need. We need to figure out what we're given, or write down what we're given. We want to be able to write out what we're trying to find, identify the missing piece that we're trying to solve for. And then we also want to write an algebraic or geometric equation that relates the variables together. So we read the problem and we have to recognize, okay, which equation are we going to use that is going to connect all these variables together? So that could be a couple of different equations here. The most common ones that we're going to see are Pythagorean Theorem, relating the sides of a right triangle. It could be area, different area formulas. It could be different volume formulas. So really, we have to read the problem to figure out, right? Maybe it's area of a square or area of a circle, or it could be volume of a sphere, the volume of a cone, right? So just being able to recognize what equation is going to be our starting point. Now, once we find our starting equation, then we differentiate. So differentiate just means find the derivative, okay, with respect to time. So a lot of times your derivative is going to be using power rule. So you're going to see with related rates, the calculus is not going to be the challenging part. It's just relatively easy power rule problems. It's the setup that requires more work. It's the cleanup that requires more work. We may see a little bit of product rule as well, but more or less, you're going to see your derivatives is going to be a little easier than the current section that we're on with chapter 2. After that, we're going to substitute and solve. So I'm going to highlight a couple of notes here, and I can always come back to this as we look at specific problems. So we want to remember that when the value is getting larger, the rate is going to be positive. Okay, if the value is getting smaller, that rate of change is going to be negative. Okay, regardless of direction. So I want to specify this because a lot of times we want to look at the motion, the direction of motion, because I know with particle motion we did that, right? Left is negative rate or negative velocity, right is positive velocity, but here left, right, up, down is not going to affect the sign of our rate. It's going to be, we have to visualize what's happening to that length. If we visualize that length getting larger or that value getting larger, we want that rate to be positive. If we visualize that value to be getting smaller, we want that rate to be negative. Okay, so direction doesn't matter. Okay, so let's read example 1, and then I will go through step by step. So number 1 says the sides of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters in length? Okay. So first, we have to recognize what equation are we dealing with? What are the variables and what is the connection between those variables? So I see the word area. I see the word square. So ultimately, I know I'm dealing with area of a square. So that's my starting point. I know that area of a square is width times width, side length times side length. I'm going to call them x's. So I'll say A is equal to x squared, right? Area is equal to side squared, x squared. So that takes care of my step 3, right? I have my equation that I'm starting with that's going to relate the variables in our problem. Okay, so the next step is we want to find the derivative. But now the complexity is, well, it's not the derivative, it's the fact that we have to attach a bunch of these differentials as we find each derivative. So if we think about A, you'll treat A like you would X, it's just a variable. So what's the derivative of A?
$2x.
Yes, yeah. So the right side is going to be 2x, but the left side is going to be what? Okay, first step is I know that this variable is to the first power. It's going to go to a constant. But I just took the derivative of A, so I have to attach a dA over dt. So this is the pattern that we're going to see as we find every derivative. So as soon as we find the derivative, we're going to attach a differential with respect to time of that variable.
So why isn't that 0?
Why isn't this 0? Okay, so yesterday, right? Yesterday I talked about we were defining A and B as constants, but here A is a variable. So we treat A like we would X or Y, right? The derivative of a variable to the first power is just 1. So this doesn't represent a constant. This is just this is a variable to the first power. Okay. It's like X to the first power, right? X to the first power is just 1. So A to the first power is also 1. Okay, now what about the right side here? What's x squared's derivative?
$2x.
Okay, 2x. but we also need to attach its own differential because time is impacting it. So we say what?
dx dt.
Good. The d over dt is always the same, but depending on the variable, we're going to fill in that space with the appropriate variable. All right. Any questions from equation to derivative? Okay, good. Let me talk about, let me try to verbalize what each of these variables mean. So dA dt is the rate of change of area with respect to time. Write that down. ROC is rate of change. X is the length of the side. And dx dt is the rate of change of the length of side length. Okay. So let's go back and let's reread the problem and see if we can assign these values to variables. Okay, so the side of a square are increasing at a rate of 5 centimeters per minute. So what do you think this 5 is going to be assigned to? Is it dA dt? Is it x? Or is it dx dt?
Is it x?
So it definitely is x related, right? It's definitely talking about the side of a square. But we see some motion involved, right? Increasing rate, centimeters per minute. So it definitely is related to the side length, but it's actually going to be what?
So it would be area?
It's referring to the side.
Oh.
So what else is there, right? That's not going to connect with the area, right? It's the side. It's the rate of change of the side length. So what other variable do we have in front of us? Right, there's 3 variables, right? There's dA dt, there's x, and dx dt. So which one do you think it is?
Is it dx over dt?
Yeah, it's dx dt.
It's
Yeah,
changing.
yeah. So dx dt. So again, the x is referring to the side length of the square, but time means that there's going to be a rate of change involved. So anytime you see centimeters per minute, rate, increasing, right, any type of a motion involvement, you know that value is going to be associated with a rate, d over dt. Okay, any questions here? The other thing I want to point out is the word increasing. The word increasing tells us that we want this rate to be a positive rate. So just be careful with these context clues here. If a problem says decreasing, then we're going to have to we're going to have to change that rate to be a negative on by our own. The problem is never going to give us a negative rate. We're going to have to make that connection with the word that is being described. So increasing is positive. So you don't need to put a positive here, but I just want to just emphasize that we are having to choose the sign of the rate based off of the description. Okay, next up, how fast is the area increasing? So what do you think we're looking for here? Or what variable is this referencing? Good, dA over dt, right? You see the word area, so definitely it's area related, but it's not going to be a static area, right? You see it increase, you see fast, right? So all these context clues indicate that, okay, it must be some sort of rate. It's got to be dA dt. So dA dt is the unknown. That's the piece, the variable that we're looking for. Okay. When the sides measure 15 centimeters in length. Now this 15 is what?
That's just x.
That's just x. So do you guys see that distinction between x and dx dt? They both are talking about sides, but one is a static value and one is a rate. So the static value is with the variable, the rate is with the d over dt because time is involved. Right. So I think we have enough information to solve for dA dt, right? That's just, anytime you have if you only have one missing variable unknown, we should be able to find that. So we'll plug into our equation here. Two times 15 times 5. Multiply that out, we get 150. So now we have to figure out what is the unit of measure for dA dt. So let's do this a piece at a time. We'll figure out the unit of measure for area. We'll figure out the unit of measure for time, and we'll just put them over each other. Okay, what's the unit of measure for area for this problem?
Centimeters squared.
Good. Area is a two-dimensional unit, right? Volume is a three-dimensional unit. Everything else is a one-dimensional unit. So area, centimeters squared. So we took care of the numerator here. What's the time component? Centimeters squared per minute, right? Okay. So area is centimeters squared. Time is minute. We have a dA over dt, so we're going to do centimeters squared over minute. Okay, questions there? Notice that we don't do centimeters per minute squared, right? That's something else, right? That's acceleration. But here, centimeters squared per minute. We want to match the appropriate unit with what's involved here. All right, any questions? Are we okay with number one? right.
Mr. Yang,
Yeah.
I looked on the website and I still can't find the 2.6 notes.
Oh, yeah. Let's see. So did you see that link that I have put in the meeting chat?
Let me see. Yeah, are those the notes?
Yeah. So that's the page that I'm going to start putting. We're starting a new unit, so I'm going to start putting notes through that page. So if you click
okay.
that, yeah, go to the top and you'll see today's date and you'll see the link.
Thank you.
Thanks. All right. Any are okay with number 1? Okay. So number 2. All right. Let's read this problem here. We have a 25-foot ladder leaning against a vertical wall. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder moving, and in what direction when the bottom of the ladder is 15 feet from the wall? So let's draw a diagram for this here. So here's my wall, here's the ground, and here's my ladder. Bottom of the ladder is being pulled horizontally away, so it's getting pulled this way. And we know that, so if you imagine this ladder sliding down, you can kind of imagine the length of this triangle changing over time, right? So that's going to be our focus. Our focus is going to be trying to figure out that relationship between the sides of this triangle. And because we're dealing with the relationship of the sides of a right triangle, we know we can use Pythagorean theorem. So I'll use variables to kind of fill in, name each of the sides, and I know my relationship between those variables is with the right triangle, Pythagorean theorem, so here's my starting point. Okay, so there's our starting equation. I know I haven't gathered the information yet, so I'm kind of doing things out of order, but I think it's helpful if we go ahead and we find the derivative. Because we find the derivative, we have all the variables in front of us, and then we can begin to kind of fill in those gaps from what the problem is giving us. So I think this is easy enough where we can do power rule for each of the terms here. So what's the derivative of x squared going to be?
(2x).
Okay, 2x. Now remember, we're still dealing with time here, so we need to attach a what?
dx over dt.
Okay, dx dt, right? dx over dt. Remember, time is going to be the overarching variable that's impacting everything here. Every of these variables are dependent variables. Time is the only independent variable, so that's why we have that d over dt. Okay, go down the line here. Y squared becomes what's power rule there?
2y dy over dt.
Good. And I think we follow that pattern with the z on the other side, right? Z squared is 2z dz dt. Right, we're just applying power rule and not forgetting about the time component. So if we look, we have 6 variables now that we got to keep track of, right? So why don't we go ahead and just list them out, and then we can go to our problem and see what we can identify. Okay, let's go back to our problem and let's read this problem together. Okay, a 25-foot ladder is leaning against a vertical wall. So what do you think that 25 is going to be assigned to? Z, right? Z, okay. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. Okay, it's definitely a rate. It's definitely a rate. So we know it's going to be d over dt. Now here's the key word there. Horizontally.
Oh, dx.
Okay, dx over dt. Right, horizontally away. You see the words pulled. You see the word rate. You see the word feet per second. You know it can't just be x, right? It's going to be dx dt. Now the other decision we have to make is every time we write down a rate, we have to decide, do we keep it positive or do we need to make it negative? So what do you guys think? So let's think about that x there. What's happening to this length here? Is this length growing? Is it getting longer or is it getting smaller? It's growing, right? So if you can imagine a length getting larger over time, you want that rate to be positive. Now I purposely drew this diagram going left because I don't want us to get confused and assume that left is negative, right is positive, up is positive, down is negative, right? The direction has no impact. It's what's happening to that length. So every problem, you're going to have to visualize it. You're going to have to picture what's happening to the value and then let that inform the decision that you make. There's not going to be, a formula where, okay, every situation is going to be increasing or decreasing. We really have to kind of have this motion in our head in terms of visualizing the change within this problem. Okay, so we keep it positive, right, because it's getting larger over time. Okay, good. Next up, how fast is the top of the ladder moving? And in what direction? So what do you think that is referring to? That's what we're looking for. That's ultimately our variable that we're trying to solve for this problem. But what is that referencing? That's dy dt, right? If you can visualize the top of the ladder is sliding down, and that vertical motion is referring to y, but it's a motion, right? It's a fast. You see moving, so it has to be dy dt. That's the unknown piece that we don't know. Now, when everything is said and done, what do you expect out of dy dt? Do you expect dy dt to be a positive or a negative rate? Okay.
Negative.
Negative because why?
Y is decreasing.
Y is decreasing, right? Not because it's going down. The direction has no impact on our decision. It's because we expect y to be decreasing. So we want that to be negative. Okay, so that should pop up on its own. We shouldn't have to adjust for that, but we'll be looking for it. Okay. When the ladder is 15 feet from the wall. Okay, where do we put that 15? That'll be x. X. Okay, so we're just doing part A for now. Any questions so far? All right. We don't have enough to plug in yet, right? There's still too many missing values. We got to figure out what y is. We got to figure out what dz dt is. And then we can plug in, right? So let's explore y first. Okay. We know we're dealing with length of a triangle here, side length of a triangle. It's a right triangle. We know what x is 15 at this moment in time. We know z is 25. So what information do we have that can allow us to solve for y?
Well, we have z.
Yeah.
X and z. So
Yeah, Pythagorean Theorem, right? We have that relationship, so let's use it. A squared plus b squared equals c squared. So we can solve for y. This is just a snapshot, right? This is a moment in time And we can figure out at that moment in time what that vertical length of that triangle is going to be. Okay, we use your calculator. I get y squared equals 400. So y is equal to 20. This is also a extension of that 3, 4, 5 triangle. It's a multiple of that 3, 4, 5 right triangle. Okay. All right, we have that figured out. Okay, let me talk a little bit about what these represent, right? dx dt, the reason why it's 3 feet per second is because this length is increasing at 3 feet per second, right? dy dt, we expect this to be a rate that is decreasing by some numeric value per second. So dz dt is talking about the rate of change of this ladder. So what do you think the rate of change is for that ladder?
0,
It's going to be 0. Okay, and why do you say 0?
because it's not going to change in length. It's
Right.
just 25 feet.
Good. So if we think about this ladder, right, it's 25 feet at the beginning of the problem. At the end of the problem, it is still 25 feet. So the rate of change of that value is 0, right? It's not changing at all. Now, this doesn't mean that every Pythagorean theorem problem with the hypotenuse will be 0. We really have to visualize the problem, right? Every problem is going to be different depending on what the scenario is. But for our scenario, we pictured this problem in motion. This length is not changing. So that's why for us, for this problem, dz dt is 0. Okay, questions? Okay, if you look, we have everything that we need, right? We have 5 variables accounted for. There's only one missing variable. We should be able to plug in and solve. Okay, so let's do that. Okay, we start cleaning our values up here. Okay, we solve for dy dt. So just like what we wanted, right? We expected dy dt to be negative because we expected this length to be decreasing, so that's what it shows up. So next question is, what is the unit of measure for dy dt? Okay. Think about the unit of measure for y, think about the unit of measure for time, and what do we get?
Negative 9/4 feet per second.
Yeah, just like x, right? Y and x and z, these are one-dimensional unit. It's not area, it's not volume, so just feet for the y and time, and then seconds for the time, so feet per second. Okay, so that's part A. Any questions there? All right, so part B, it says, at what rate is the area changing when the bottom ladder is 15 feet from the wall? Okay, what shape are we dealing with here? Triangle again, right? So we're dealing with area of a triangle. What's the formula for area of a triangle? Okay, good. 1/2 base times height. If you think about a rectangle, right? You know a rectangle is just base times height. But you can, if you visualize yourself cutting that rectangle in half, you see half of a rectangle, so 1/2 base times height. But rather than using 1/2 base times height, we're gonna use the variables that we started with, so we don't. It'll be easier to match because we're gonna need this information to plug in. So we know we're dealing with area of a triangle. So I'll start off with area is equal to 1/2 base times height, but instead of b and h, I'm going to use x and y. Okay. It says, at what rate is the area changing? So what do you think, what variable do you think we're looking for? Ultimately, we're looking for what variable? It may not be showing up right now, but that's what we're looking for.
A.
Okay, it's definitely area related.
Is it dA over dt?
Okay, why do you say dA dt?
Because it's not a constant and it's
Yeah.
the area.
It's rate, right? It's not a static value, right? Rate changing. You see those words describing area, you know there's going to be a derivative. So you know we're looking for dA dt, which means we're going to find the derivative, right? So a, which become 1 dA dt. So we know that's the derivative of a. But the derivative of this side, can we just rely on power rule, or is there something more that we need to account for?
Product rule?
Yeah, we need to use product rule. Do you see how x and y are two separate variables? They're being multiplied. We can't merge them together. So we're stuck with two variables being multiplied, and the way that we deal with two multiplied terms for derivative is product rule.
Wait, Mr. Yang,
Yes,
how did you get the half xy though?
the half xy. Okay, so we know we're dealing with an area of a triangle. So I built that formula. The area of a triangle is 1/2 base times height.
Okay, thanks.
Yeah, because you know a rectangle is just base times height. So a triangle is just going to be half that. So 1/2 base times height. And then I just used x and y because those are the variables that we kind of built our problem on. Okay, we said product rule, right? So f prime g plus fg prime. Okay, so now we're going to fill in those blanks, those spaces. Okay, what's f prime going to be? What's the derivative of 1/2 x? Yep, it is just 1/2, but remember time is still involved, right? So we still need to include what? Dx.
Dx dt.
Good, yeah. Okay.
So I'm just wondering, When do we have to put like dx dt or dA dt?
Sorry, can you repeat that question again?
So when are we required to put like dx dt or dA dt, like the derivative symbol?
When we're dealing with related rates, if there's time involved in the problem, then we're always going to have a d over dt.
So like if we're looking at a variable that's going to change over time.
Yes, that's right. Yeah. Anytime there's a variable changing over time, and time is going to be the underlying variable for all these problems. So we're going to have d over dt for every one of these variables that pop up. Okay. All right, so let's
Thank
fill
you.
in the G portion. No changes, right? F portion, no changes. And what's G prime going to be? Okay, but it's dy over what? dy over...
Or dy over dt.
Good, all right, dy over dt. Yeah, implicit will be dy over dx, but because time is what we're dealing with here, is dy over dt. Yep, so y becomes 1, and then we attach a dy over dt. Okay, so take a look here. Any questions? Is there anything that you want me to clarify or something that doesn't quite make sense? Okay, so now we just want to plug in, right? We have all the information from part A can be used because we're talking about the same scenario, right? 15 feet from the wall, same everything. So we just put in that information. Okay, clean this up. Use our calculator. I'm sorry, we have dy dt, right? Sorry, dy dt is negative 9/4, so we can fill that in. That's not unknown anymore. Okay, so 30 minus 135 over 8. In the calculator, I get 105 over 8. So the next piece that we have to figure out is our unit of measure. What's the unit of measure for dA over dt? Okay, so let's think area. Let's think time. And we just put them over each other. So what's the area unit?
Feet per second. Or feet squared.
Yeah.
Per second.
Feet squared per second. All right, sorry. Okay, so area is a two-dimensional unit, so square feet. Time is seconds, so square feet per second. Okay, so that's as far as I want to get with related rates. We can pick this up next Thursday. I want to do some chapter 2 review. But any questions so far? We just kind of got our feet wet with related rates. But they're all going to kind of follow the same pattern, right? We start with an equation, we find the derivative, and then we start pulling information or gathering information and putting it in. Okay, so I want to do one problem from the test review. Monday, we're going to do a full review day. Tuesday will be your test. Wednesday is asynchronous day, and then Thursday we're going to come back to related rates.
Is there going to be any related rates on the test?
No, this is 2.6, so your test is just 2.2 through 2.5. Yeah, this is not on the test. I just wanted to get ahead of our schedule here, or to keep up with our schedule. Okay, let's go to our test review. So on this test review sheet, if you guys can flip to the back and go to number 9. If you can cross off number 7 and 8, these are from 2.1. We're not going to have that. Okay, so let me let's read through number 9 here. Number 9 says, find the point at which the equation of the graph has a vertical or horizontal tangent line. So first up, I know I have to involve derivative. But if I look at this equation, I see that this is not a function that we're used to seeing, right? It's not y equals and everything else on the right is x. We have a mixture of y's. The y's are inserted within the x's. So we know we have to involve implicit, right? This is most likely not a function. So we got to do implicit here. And with implicit, we know we're going to have a bunch of dy dx that comes up along the way. For the y's, right? For the y's, we will have dy dx. Okay, so let's go through and find the derivative of each term. So we can build our derivative equation, and then we can get to our vertical and horizontal. Okay, actually, let me recap how we find vertical and horizontal tangent. So vertical tangents, this is where slope of the graph is undefined. These vertical tangents. So let's say this graph, actually this is what the graph it's going to be an ellipse. So do you see vertical tangents here? Right, it's going to be here on the side, right? So this is how we find these vertical tangents. We're going to be setting the denominator of dy dx equal to 0. So here's our strategy. We're going to set the denominator of dy dx equal to 0. And when we solve for that variable, we're able to locate the places where these behaviors are occurring. Okay, horizontal tangents, these are places where slope is 0. And the way we find places where there's a slope 0 is we set the numerator of dy dx equal to 0. So if you look on this ellipse here, we're expecting 2 points, right? So we're essentially, if we set the numerator of dy dx equal to 0, we're able to locate these places where there's a slope 0. I just wanted to kind of give some visual as we go through it. Okay, so, but before we can do any of this, we got to know what dy dx is, right? We have to work our way down to dy dx, our derivative first. Okay, so let's begin our derivative process here. Every term, I think, is just power rule, right? We don't have any messy rules to deal with. Now, no product, no quotient. So let's go through each term at a time here. Okay, what does 4x squared turn into? Well, just 8x, right? And also with implicit, we don't do anything additional with x's, right? It's just the y's that we got to do anything additional. Okay, y squared becomes? Yep, 2y dy dx. All right, minus
Eight.
Plus, what does 4y turn
4
into?
dy dx.
Good. We took the derivative of y, so dy dx has to pop up, even though the y disappears. Okay. Do we keep the 4 or what? Drop it to be 0, right? So don't forget, constants, we got to convert constants to be 0. Okay, so that's solve for dy dx. I'm going to keep these terms on the left so I can factor it out and then divide over. Okay, factor dy dx out. Divide the parentheses over. So here's our dy dx. If you want to continue factoring out the 2 and reduce it, that's fine, but this is okay. So now that we have dy dx, we can look for these specific locations, right? We can find vertical tangent by looking at the denominator, setting that equal to 0, and find the location for that. So vertical tangent. Denominator is this 2y plus 4. Set that equal to 0. Subtract 4, divide by 2. Okay, we don't have the full location yet, but at least we have something location related. So we'll come back to it. Okay. Horizontal tangents. Now we focus our attention at the numerator portion. We set the numerator equal to 0. Okay. This says find the points, right? We can't just say 1 and -2 and call that the point, right? There's a lot more than that, right? There's 2 vertical tangents, and we have 2 horizontal tangents. So how do you think we can find the locations? Because it's asking for the point, so we want to find the physical location. Because right now we only have just a piece of the information. Do we have anything available to help us find those locations?
Would we plug them into the original equation?
Okay, why do you plug into the original and not into the derivative?
It would probably describe like the physical location better,
Good.
the original one.
Right, so yeah, so I want to keep that in our heads, right? That we want to know what the purpose of each of these equations does for us, right? This, if we plug in a value, it's going to give us a number. That number is not location. That number is slope related. But if I want to find the physical location, that is going to go to the original starting equation there. Good. So this is what's going to happen. If I plug -2 in for y, I'm going to solve for x. And when I solve for x, I'm going to get 2 x values. And then those 2 x values is going to help me locate these points, right? They both have the same y value, but then we solve for x, and that's what we get. Same thing here. If I plug 1 in for x and I solve for y, the algebraic step is going to help me solve for y. I'm going to get 2 y values, and I'm going to get 1 comma the y value and 1 comma another y value. So that's going to help us pinpoint these. Okay, so I'm running out of time, so I was not able to. I can finish this on Monday, but I kind of just quickly show you what I did with the previous period. Right, we took that -2, plug it into the equation, we solve for x, and then there's our order pairs: 0, -2, and 2, -2. For horizontal tangent, we took that 1, plug into the equation, solve for y, we got 0, -4, so there's our 2 order pairs: 1, 0, and 1, -4. All right, I'm going to have morning review on Monday and Tuesday, but I'm going to give you guys a little bit of homework just so that we're keeping these concepts fresh in our minds. So off the miscellaneous worksheet that we're working off of, these are, remember we did these problems involving graphing and product and chain and quotient. So the 5th page of it has FRQ, free response question, that is implicit related. So just have you guys try this problem here, number 5 on page 5. Okay, I also released all the quizzes back to you. So Monday, maybe I can spend Monday morning going over if you have any questions about the quiz, but hopefully the comments I made is specific enough where you know the mistakes that you made. But I want you guys to be able to ask me questions if you have any. All right, thanks everyone. Hope you guys have a great day. I'll stick around if you have any questions. Otherwise, have a great weekend. See you guys.
Thank you.
Thank you.
Have a good weekend.